If you've ever driven or ridden in an automobile, there's a near 100% chance you've hit a bump in the road as you transition onto or off of a bridge. In fact, some studies estimate that it happens on a quarter of all bridges in the US. It's dangerous to drivers and expensive to fix, but the reason it happens isn't too complicated to understand. It's a tale almost as old as time. You need a bridge to pass over another road or highway, but you need a way to get vehicles from ground level up to the bridge. So you design an embankment, a compacted pile of soil that can be paved into a ramp up to the bridge. But here's the problem. Even though the bridge and embankment sit right next to each other, they are entirely different structures with entirely different structural behavior. A bridge is often relatively lightweight and supported on a rigid foundation like piles driven or drilled deep into the ground. An embankment is, if the geotechnical engineers will forgive me for saying it, essentially just a heavy pile of dirt. And when you put heavy stuff on the ground, particularly in places that have naturally soft soils like swamps and coastal plains, the ground settles as a result. If the bridge doesn't settle as much or at the same rate, you end up with a bump. Over the years, engineers have come up with a lot of creative ways to mitigate the settlement of heavy stuff on soft soils, but one of those solutions seems so simple that it's almost unbelievable. Just make embankments less heavy. Let's talk about some of the bizarre materials we can use to reduce weight and a few of the reasons it's not quite as simple as it sounds. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about lightweight fills. This video is sponsored by HelloFresh. More on them later. The Latin phrase for dry land, terra firma, literally translates to firm earth. It's ingrained in us that the ground is a solid entity below our feet, but geotechnical engineers know better. The things we build often exceed the Earth's capacity to withstand their weight, at least not without some help. Ground modification is the technical term for all the ways we assist the natural soil's ability to bear imposed loads. And I've covered quite a few of them in previous videos, including vertical drains that help water leave the soil, surcharge loading to speed up settlement so it happens during construction instead of afterwards, soil nails used to stabilize slopes, and one of the first videos I ever made, the use of reinforcing elements to create mechanically stabilized earth walls. One of the simplest definitions of design engineering is just making sure that the loads don't exceed the strength of the material in question. If they do, we call it a failure. A failure can be a catastrophic loss of function, like a collapse, but a failure can also be a loss of serviceability, like a road that becomes too rough or a bridge approach that develops a major bump. Ground modification techniques mostly focus on increasing the strength of the underlying soil, but one technique instead involves decreasing the loads, allowing engineers to accept the natural resistance of a soft foundation. Let me put you in a hypothetical situation to give you a sense of how this works. Imagine you're a transportation engineer working on a new highway bridge that will replace an at-grade intersection that uses a traffic signal, allowing vehicles on the highway to bypass the intersection. This is already a busy intersection, hence the need for the bypass, and now you're going to mess it all up with a bunch of construction. You design the embankments that lead up to the bridge to be built from engineered fill, a strong soil material that's about as inexpensive as construction gets. You hand the design off to your geotechnical engineer, and they come back with this graph, a plot of settlement over time. Let's just say you want to limit the settlement of the embankment to 2 inches or 5 centimeters after construction is complete. That's a pretty small bump. This graph says that to do that, you'll have to let your new embankment sit and settle for about 3 years before you pave the road and open the bridge. If you put this up on a PowerPoint slide at a public meeting in front of all the people who use this intersection on a daily basis, what do you think they'll say? Most likely, they're going to ask you to find a way to speed up the process, politely or otherwise. From what I can tell from my inbox, a construction site where no one's doing any work is a commuter's biggest pet peeve. So you start looking for alternative designs, and you remember a key fact about roadway embankments. The weight of the traffic on the road is only a small part of the total load experienced by the natural ground. Most of the weight is the embankment itself. Soil is heavy. They teach us that in college. So what if you could replace it with something else? In fact, there is a litany of granular material that might be used in a roadway embankment instead of soil to reduce the loading on the foundation. And all of them have unique engineering properties. In other words, advantages and disadvantages. Wood fibers have been used for many years as a lightweight fill with a surprisingly robust service life of around 50 years before the organic material decays. Similarly, roadway embankments have been seen as a popular way to reuse waste materials. In particular, the state of New York has used shredded tires as a lightweight fill with success, so far avoiding the spontaneous combustions that have happened in other states. There are also some very interesting materials that are manufactured specifically to be used as lightweight fills. Expanded shale and clay aggregates are formed by heating raw materials in a rotary kiln to temperatures above 1,000 Celsius. The gases in the clay or shale expand, forming thousands of tiny bubbles. The aggregate comes out of the kiln in this round shape, and it has a lot of uses outside heavy civil construction like insulation, filtration, and growing media for plants. But round particles like this don't work well as backfill because they don't interlock. So most manufacturers send the aggregate through a final crushing and screening process before the material is shipped out. Another manufactured lightweight fill is foamed glass aggregate. This is created in a similar way to the expanded shale, where heating the raw material plus a foaming agent creates tiny bubbles. When the foamed glass exits the kiln, it is quickly cooled, causing it to naturally break up into aggregate-sized pieces. You can see in my graduated cylinders here that I have 1 pound, or about half a kilogram, of soil, sand, and gravel. It takes about twice as much expanded shale aggregate to make up that weight, since its bulk density is about half that of traditional embankment building materials. And the foamed glass aggregate is even lighter. All these different lightweight fills can be used to reduce the loading on soft soils below roadways and protect underground utilities from damage, but they also have a major advantage when used with retaining walls: reduced lateral pressure. I've covered retaining walls in a previous video, so check that out after this if you want to learn more, but here's an overview. Granular materials like soil aren't stable on steep slopes, so we often build walls meant to hold them back, usually to take fuller advantage of a site by creating more usable spaces. Retaining walls are everywhere if you know where to look, but they also represent one of the most underappreciated challenges in civil engineering. Even though soil doesn't flow quite as easily as water does, it is around twice as dense. That means building a wall to hold back soil is essentially like building a dam. The force of that soil against the wall, called lateral earth pressure, can be enormous, and it's proportional both to the height of the wall and the density of the material it holds back. Here's an example. When Port Canaveral in Florida decided to expand Terminal 3 to accommodate larger cruise ships, they knew they would need not only a new passenger terminal building, but also a truly colossal retaining wall to form the wharf. The engineers were tasked with designing a wall that would be around 50 feet or 15 meters tall to allow the enormous cruise ships to dock directly alongside the wharf. The port already had stockpiles of soil left over from previous projects, so the new retaining wall would get its backfill for free. But holding back 50 feet of heavy fill material is not a simple task. The engineers proposed a combi wall system that's made from steel sheet piles supported between large pipe piles for added stiffness, in addition to a complex tieback structure to provide additional support at the top of the wall. When the design team considered using lightweight fill behind the retaining wall, they calculated that they could significantly reduce the size of the piles of the combi wall, use a more commonly available grade of steel instead of the specialty material, and simplify the tieback system. Even though the lightweight fill was significantly more expensive than the free backfill available at the site, it still saved the project about $3 million compared to the original design. The fill at Port Canaveral and all the lightweight fills we've discussed so far are granular materials that essentially behave like normal soil, sand, or gravel fills, just with a lower density. They still have to be handled, placed, and compacted to create an embankment or retaining wall backfill, just like any typical earthwork project. But there are a couple of lightweight fills that are installed much differently. Concrete can also be made lightweight using some of the aggregates mentioned earlier in place of normal stone and sand, or by injecting foam into the mix, often called cellular concrete. On projects where it's difficult or time-consuming to place and compact granular fill, you can just pump this stuff right out of a hose and place it right where it needs to be, speeding up construction and eliminating the need for lots of heavy equipment. There are a few companies that make cellular concrete, and they can tailor the mix to be as strong or lightweight as needed for the project. You can even get concrete with less density than water, meaning it floats. This test cylinder was graciously provided by Cellcrete, so I could give you a close-up look at how the product behaves. Of course, we should try and break it. Let's put it under the hydraulic press and see how much force it takes. The pressure gauges on my press showed a force of just under a ton to break this sample. That is equivalent to a pressure of around 200 psi, or 1.4 megapascals, much stronger than most structural backfills. You're not going to be making skyscraper frames or bridge girders from cellular concrete, but it's more than strong enough to hold up to traffic loads without imposing tons of weight into a retaining wall or the soft soils below an embankment. The last lightweight fill used in heavy civil construction is also the most surprising: expanded polystyrene foam, also known as EPS and colloquially as styrofoam. When used in construction, it's often called geofoam, but it's the same stuff that makes up your disposable coffee cups, mannequin heads, and packaging material. EPS seems insubstantial because of its weight, but it's actually a pretty strong material in compression. About 7 years ago, I used my car to demonstrate the compressive strength of mechanically stabilized earth. Well, I still have that jack, and I still drive that car. So let's try the experiment with EPS foam. This is probably around 500 to 600 pounds, and there is some deflection, but the block isn't struggling to hold the weight. In an actual embankment, the pavement spreads out traffic loads so they aren't concentrated like what's shown in my demonstration, to the point where you would never know that you're driving on styrofoam. EPS foam has some cool benefits, including how easy it is to place. The blocks can be lifted by a single worker, placed in most weather conditions, don't require compaction or heavy equipment, and can be shaped as needed using hot wires. But it has some downsides too. This material won't work well for embankments that see standing water or high groundwater because of the buoyancy. The embankment could literally float away. They're also so lightweight that you have to consider a new force that most highway engineers don't think about when designing embankments: the wind. Also, because EPS foam is such a good insulator, it creates a thermal disconnect between the pavement and the underlying ground, making the road more susceptible to icing. Finally, EPS foam has a weakness to a substance that is pretty regularly spilled onto roadways. It dissolves in fuel. If a crash, spill, or leak were to happen on an embankment that uses EPS foam without a properly designed barrier, the whole thing could just melt away. Even with all those considerations, EPS foam is a popular choice for lightweight fills. We even have a nice government report on best practices called Guideline and Recommended Standard for Geofoam Applications in Highway Embankments, if you're looking for some lightweight bedtime reading. It was used extensively in Seattle on the replacement of the Alaskan Way Viaduct to avoid overstressing the landfill materials that underlie major parts of the city. Thousands of drivers in Seattle and millions of people around the world drive over lightweight embankments, probably without any knowledge of what's below the pavement. But the next time you pass over a bridge and don't feel a bump transitioning between the deck and roadway embankments, it might just be lightweight aggregate, cellular concrete, or geofoam below your tires working to make our infrastructure as cost-effective and long-lasting as possible. Speaking of lightweight, one of my goals in 2023 is to keep eating healthy meals for dinner. That's a lot easier with HelloFresh, sponsor of this channel since 2019, which means my wife and I have been filming ourselves cooking dinner for 4 years now. Sometimes we do it as part of the bedtime hustle, and sometimes we wait until the kids go to bed and treat it like a date night. That has its benefits, but it has its downsides too.
I'm hungry. I'm hungry. Did I mention that I'm hungry? Does it say to do them one at a time? Baby, I'm hungry.
Luckily, HelloFresh's latest line of meals, called Fast and Fresh, are ready in around 15 to 20 minutes. That's faster than if you order delivery and way faster than going to the grocery store, which means we have a lot more time to spend doing things we love and spending time with the people we love too. HelloFresh sends pre-portioned ingredients and easy-to-follow recipe cards so you don't have to be an expert chef or even very good at cooking at all.
Why don't you just turn your bread upside down and rub it in that?
You can turn cooking from a chore to your favorite thing to do on date night or any night with HelloFresh. And right now they have a really nice discount for anyone who wants to try it out. Go to HelloFresh.com and use code PRACTICAL65 to get 65% off plus free shipping. We obviously love this service, and I think you will too.
I don't know if you're aware, but I'm hungry.
That's HelloFresh.com and use code PRACTICAL65 at checkout to support the channel and try something fun and new for the new year. Thank you for watching, and let me know what you think.